All right. So we've covered the proximal tubule, and moving on to the loop of Henle, which consists of really of three different portions. There's a descending limb. There is a acute 180-degree turn, and then the ascending limb. The vast majority of the glomeruli have very short descending loops, or short loops. There are a few of them, though, that are what are known as juxtamedullary nephrons that have very long loops, and we actually call the peritubular capillary that is adjacent to it the vasa recta, kind of a specialized name. It's this drop down into the medullary portion that creates a osmotic pressure change in these long loops that are responsible for an additional amount of water to be reabsorbed. And I'll go through that slowly because it's a little bit confusing. I have to review it every time I give this lecture because I always get it mixed up a little bit. So let me do this. Let me go to the ascending loop first. I'll come back to the descending. So if you look at our picture here, this is part of the loop where, and again, this is out of Egan. Remember Egan? The song's about Egan. You guys don't get the joke there, but that's okay. And you can see that as it gets further and further down into the medullary region. I want to say medulla, but that kind of would be correct, but don't like saying that. But the osmolarity goes up significantly. As osmolarity goes up, that means that you have more tendency to pull fluid out of the tubule and into the vascular space. The reason why this osmolarity is so high is that, first of all, this portion of the loop, the ascending loop, is impermeable to water. So there's no water moving out, but what you do have is sodium being pumped out of the tubule and into that area. So sodium moves out of the tubule and basically just saturates this area. And sodium, as we'll see, is a very high osmotic pressure. When that sodium is there, the tendency of water to follow it is very great. Problem is that it can't do it in the ascending loop because the loop is impermeable to water. So that high level of sodium then causes that environment to want to promote water movement. The descending loop is permeable to water and impermeable to ions. So this is where another 25% of the water is reabsorbed. 65% was reabsorbed in the proximal convoluted tubule. Here's another 25% that ends up happening. And again, it's because of that high sodium content that we end up having that high osmotic pressure and lots of more water pulled off. Does that make sense? Yes. Yeah, this is being recorded. They call this a countercurrent multiplier. And it's just basically that you get a lot more bang for your buck because of that sodium being present. Okay. Finally, then, we have a couple of the last bit of water that is reabsorbed. And this is back into the cortex now, so we've crossed back over that boundary, and we're back up into this final bit here. And this is really where any sodium that has not been reabsorbed now is reabsorbed, along with some other ions. And this is also where you have what's called the juxtaglomerular apparatus, where that duct passes by the peritubular capillaries, the afferent arteriole and the efferent arteriole, leading into the glomerulus, and that has a special function also we'll talk about next time when we talk about aldosterone. So it's kind of designed to, first of all, pick up whatever water needs to be reabsorbed, whatever it can, but it also, that passing by those arterioles affects water balance, as we'll see, with aldosterone and ADH. So this is the second place where sodium is primarily reabsorbed. We had the first one was in the proximal convoluted tubule, where it was reabsorbed as sodium chloride, and that also happens here. Sodium comes back, chloride comes back. And again, this is a primary active transport, so it's going to require some energy. If we are hypochloremic for whatever reason, we're going to reabsorb through secretion of either a positive ion hydrogen or a positive ion potassium. In the first case, when chloride's not available, we end up having, I got on the next slide, I think. Yeah. In the case of the hydrogen ion, we have CO2 coming in. Remember, there's the presence of carbonic anhydrase within the renal tubule, one of three places in the body where it's located. Does anybody remember where the other one might be? Yes, in the erythrocyte. Other place that carbonic anhydrase is found inside the erythrocyte. Does somebody know the third? In the eye. Interestingly enough. Okay, so in the presence of carbonic anhydrase, CO2 and water forms carbonic acid, dissociates into bicarbonate ions and hydrogen ions. If there's not enough chloride to be secreted back, the sodium comes back with bicarbonate. So there's a sodium bicarbonate reabsorption. Sodium gets reabsorbed, but we sacrifice the hydrogen ion. In sacrificing the hydrogen ion, then, we end up having a blood that's a little bit alkalotic. And we'll find that one of the metabolic alkalemias we can divide into those that have a hypochloremia and those that don't, as we go. So primary way, sodium chloride. Secondary way, sodium bicarbonate when we don't have enough chloride, and we can give up the hydrogen ion. And then there's a third mechanism where we're sacrificing potassium if I don't have excess hydrogen ions available. Let's say I already have an alkalemia for some reason or other. I can't give up the hydrogen ion. I want to reabsorb the sodium. It's going to come back in exchange for a direct sodium-potassium exchange, one cation for another cation. In that case, what you end up having is potassium being excreted. And this is an instance where you can end up having hypokalemia developing. It's one of the causes of hypokalemia is an alkalemia and hypochloremia together, and you end up having that situation where all you got left to give up is potassium. Okay. Sodium chloride, primary. Sodium bicarbonate, where we lose the hydrogen ion, and direct exchange potassium for sodium, just through the sodium-potassium pump. Okay. 3 ways sodium is reabsorbed. That might make a good test question. Just saying. Don't tell Luke. So 65% in the proximal convoluted, 25% in the descending loop of Henle, 10% in the distal tubule, and that should add up to 100%. There is some minor amount of water that's still exchanged in the collecting tubule before it gets to the ureter. It's not significant for our purposes here. Got it? It's going to become important because when we talk about diuretics, diuretics work in different portions. Some in the proximal, some in the descending loop, some in the ascending loop, some in the distal loop. So, or distal convoluted tubule, I should say. Okay. Let's, I think this is what we just talked about. Sodium chloride via active transport. Another 20% is sodium bicarbonate, and that can exist either with the loss of hydrogen ions or loss of potassium ions. This, by the way, is the way the kidney also regulates bicarbonate ions themselves. So if it needs to retain or dump bicarbonate ions, it does it through using that secondary sodium. It does it by allowing the bicarb to not be reabsorbed or reabsorbs excess if it happens to have an acidosis. All right. First of all, I'm not going to test you on this because you may or may not have ever had this before. But let's go back and review some of these concepts. Some of this is from 106. Some of it is just, you might have picked it up in a college or high school chemistry or physics, chemistry or biology course. The term mole. The term mole refers to the number of particles present. And we know that according to Avogadro's law, 6.022 times 10 to the 23rd particles. In addition, if we're talking about a gas like oxygen, we know that a mole of oxygen occupies 22.4 liters. Does anybody know the exception to that? The all gas. It is CO2. It's like 22.3 or something weird. The mass of one mole is dependent upon what we're talking about. So to calculate the formula mass, we just figure out what it is in atomic mass units by looking at a periodic table, substitute grams for the unit of measurement, and we're done. So a molecule of sodium has a mass of 22.99 atomic mass units. A mole of sodium then would have 6.02 times 10 to the, what did I do there? Times 102 times 10 to the 23rd. It should be particles, and weighs 22.9 grams. So all we're doing is just substituting units there. There is a term called molarity, which is related to how many moles of solute you have dissolved in solution. So how many moles per liter of solution. A 1 molar solution contains 1 mole of solute, whatever that solute is, sodium chloride, whatever, in 1 liter of solution. The term millimolar or millimoles is basically a thousandth of that. And then finally, the term equivalent. An equivalent talks about how much of a substance is required to combine with 1 mole of hydrogen ions. In an example of chloride, 1 mole of chlorine, or 1 mole of chloride ions, I probably should say, they combine in a 1-to-1 relationship so that 1 mole of hydrogen combines with 1 mole of chloride to form hydrochloric acid. So we're going to talk about that extra chloride that is needed, 1 mole, as 1 equivalent. In an example of calcium chloride, you end up having 2 moles of chloride mixing with 1 mole of calcium. So we would say that a half a mole of calcium is one equivalent in that. This is where that term milliequivalent comes from, because you're looking at a 1/1000th of that equivalent that would be there to mix with the hydrogen ions. All right, and just as a review, this you should know. No, I'm not going to, that's on chemistry, but just so you know where those terms, where does milliequivalent come from? When I talk about a 2 molar solution, and if you look at your IV bags, you'll actually see this. Where's that coming from? What depends, or what determines that osmotic pressure is basically a combination of number of particles present and whether or not those particles are as compounds or as ionic solutes. So in the case of sodium chloride, We know that 1 mole of sodium and 1 mole of chloride mix together, and when they're placed into solution, they dissociate out, so you really have 2 particles that are there. Where in the case of glucose, even though it's a bigger molecule, it doesn't break itself off into ionics. It's covalent bonding that you end up having in glucose, so you end up having basically only 1 particle. Even though it's a big particle, there's twice as many sodium and chloride particles as there are glucose particles. So this term that we use to talk about how much osmotic pressure is created is osmolarity. And the unit, for those who care, I don't, it's called an osmole. And yes, we can divide it by 1,000 to get a milliosmole. And units that have equal osmolarity will have equal osmotic pressure, equal amounts of pull that they exert in the process. When we have a change in osmolarity, that's one of the things that promotes the movement of fluid. If I don't have as high of osmolarity in the vascular space, water's going to leak out of it. And it's going to leak into the interstitial space and eventually into the cell as that concentration changes. Additionally, when we have that fluid movement out of the vascular space and into the interstitial space, when water leaves, you also then have a change in electrolyte concentration, because the concentration is always related to how much volume you have. What is the units for sodium? When you look at a lab slip, what does it say for sodium? What's it for bicarbonate? Per liter. So if I change the number of liters I have, I change the concentration of that value. Okay? It's going to become very important when we look at some of the electrolyte values. It's not necessarily that the electrolyte amount has changed, it's the amount of water which has changed, yeah.
But wouldn't the higher concentration draw that water back in?
Not necessarily. Not if something else is pulling it out that's got a greater osmolarity. If it was just that in isolation, yes. But if something else is on the other side pulling, and it's pulling harder, it's not going to be able to pull it back in again. All right. Normally, we take in about a little over 2,500 milliliters of water per day. Majority of that is as, well, not a real significant majority, but some of it, as fluids, the rest of it as part of our food intake. And there's some water which is created just through metabolic activity. Remember, as you digest carbohydrates, you produce CO2 and water as a byproduct, so there's some amount of water that is created there. Have you ever heard of the term, you should drink 8 ounces of water 8 times a day, and it can't be coffee or juice? Bull. Totally false. Totally false fallacy. Your body will tell you when you're dehydrated or when to drink more water. Okay, and it roughly is about 2,500. 8 ounces, 8 times a day, roughly is the right amount of water. But remember, we're getting a lot of fluid into our bodies, a lot of water into our bodies as food. So you don't have to overdo it. Dana?
Should we know, like, the parts of the food and
I think you should know that normal intake's about 2,500, and roughly half of it is fluids. Because why? When we have a patient in the ICU who's now NPO, how are they getting their fluids? They're not eating. So about almost half of the fluid intake has to be replenished through some other fashion. We lose water. Look at that. It's the same amount of water. So what we take in, we should be putting out. Big duh, right? I should match O. And again, good portion of it is urine. But there's some also in fecal matter, and there's some of it, we don't really think about this a whole lot, but as we exhale, we're exhaling humidified gas, and there's some amount there. That is known as insensible water loss. Not insensitive, that would be me. Insensible water loss. It's water loss through humidity, perspiration, something along that line. Anytime we have excessive amounts of blood volume loss within the body, we're going to classify that as hypovolemia. It could be because we have bleeding directly, as you might see during traumas or obstetric emergencies where there's excessive vaginal bleeding. We can also just have it from loss of bodily fluids, diarrhea, vomiting, excessive use of diuretics, burns where they're third spacing going out of the vascular space. It's one of the complications of Ebola. Most of the people who die from it die from dehydration, and just you can't keep up with the rehydration because there's just massive diarrhea, massive vomiting. We also can recognize this, obviously, by a reduced urine output as the primary area, but you'll also see the mucous membranes drying out. And novel idea, treatment for it is prevent what's being lost and rehydrate them. And as we'll find out in 24-20 next semester, this is one of the ways that you can end up having a shock state present, is hypovolemic shock. Other end of the spectrum, hypervolemia, usually is associated with some problem with either excretion or some other metabolic problem, like hyperaldosteronism and congestive heart failure. Symptoms, again, you guys should be pretty familiar with crackles, development of edema, jugular venous distension, high blood pressure, ascites. And the treatment is to find the cause and fix it, and we can use diuretics to relieve some of that. You should know the normal range for sodium. We know that it's the greatest extracellular cation, and we know that it's been really important with fluid balance, as we just saw within the kidney. When the sodium is reabsorbed in most cases, you end up having water reabsorbed with it. It also has some function with muscle contraction. If you think about the cardiac cycle, you know that it's the influx of sodium into the myocardial cell, the efflux of potassium that causes that depolarization process. Low sodium levels, below 135. This is actually one of the more common electrolyte disorders and also one of the worst ones. Typically, it's not so much that you've lost sodium as that you have a dilutional issue, too much fluid administration, and you end up, since it's in milliequivalents per liter, if you make that liter value higher, the amount of sodium that is there, the actual number of particles, just becomes more dilute in the process. As far as some of the what the person would present with, for the most part, I'm not concerned about, because they're all kind of the same thing. Death being the final door that is there. And obviously, if my sodium's low and my it's not something where I have a large blood volume, you would want to give them some sodium back. Hypernatremia is typically the opposite end of the spectrum, is usually caused by dehydration, especially if we're looking at a group of diuretics called osmotic diuretics that we'll talk about next time. They have huge shifts in water and in the process sodium. Anytime you have excessive urination, like you would have with diabetes, either diabetes mellitus or diabetes insipidus, and obviously I just want to correct it with fluids. Potassium, you should know the normal level is 3.5 to 5. Again, it's important for electrical muscle contraction, especially cardiac. Hypokalemia can be caused by excessive urine output. There's a lot of metabolic disturbances that can alter potassium. This is one that I think you should know, this bullet point here, that you end up having flat or inverted T waves with hypokalemia. And the solution is to give them back some potassium. That's a pretty big duh. Hyperkalemia, and again, it's not a linear situation in the sense that the body deteriorates rather rapidly as the potassium level rises. We see this a lot with renal failure. We also see it, hyperkalemia, when we end up having potassium leaking out of the cell, as we see with burns and rhabdomyolysis. And again, EKG is something you should know. That we end up having tall peaked T waves. We treat hyperkalemia by trying to push the potassium back into the cell. We can do that by giving calcium, typically calcium gluconate. We can do it by giving insulin and D50. We can do it by trying to treat with sodium bicarbonate. And we can do it by our wonderful albuterol. So a continuous nebulization of albuterol will reverse hyperkalemia because one of the side effects is potassium loss. And in really severe cases, we can do hemodialysis. When we talk about pulseless electrical activity, one of the causes of pulseless electrical activity can be hyperkalemia. And we'll a lot of times see the heart become very ineffective as a pump in those states. And rapid reversal is needed. And finally, chloride, normal value you should be aware of. It is the major, and by the way, potassium is the major intracellular cation. This is the major extracellular cation. Anion. Has a lot of other functions that is there. We know that it control of bicarbonate is with a chloride shift, and I'll make mention of it now, and we'll talk more about it later. We use what is known as the Bronsted-Lowry mechanism for determination of pH. We're looking at the Henderson-Hasselbalch equation. There is a totally different approach to acid-base interpretation called the Stewart's approach to acid-base. And he does it by looking at difference between strong ions, and chloride is one of the big strong ions. If you ever really want to get confused, it's an interesting approach. Many people feel it's a better way to determine pH. I'm not so sure. I don't want to learn anything more. My brain hurts. Low chloride levels usually you see with loss of hydrochloric acid, vomiting, excessive GI drainage. It kind of goes hand in hand with sodium, so that if you see a hypernatremia, you probably got a hyperchloremia also. And we treat it by giving chloride back and sodium chloride. High levels of chloride typically is, again, similar to sodium, is excess fluids on board. Not so much that the value itself is necessarily high. And fix the cause. Did you ever see these series of pictures? They're amazing. Guy took a high-speed underwater photograph of a dog going after a ball, and some of them are just wild. Looks like a rabid dog.